radioactivity, glow-in-the-dark green ooze that gives you superhuman powers, right? Well, in high school physics, it's more about learning how to do things like balance nuclear decay equations. So today, I'm going to give you the superhuman powers to make balancing nuclear decay equations fun and easy. So the first type of nuclear decay equation we're going to look at is alpha decay. An alpha particle is the same as a helium nucleus in that it's comprised of 2 protons and 2 neutrons, as you can see here. There are 2 different ways of representing an alpha particle in chemical symbols. You can either use the chemical element for helium, as you can see here, or you can use the Greek letter of alpha, as you can see here. Which method you use may not matter at all, but you should check with your specific exam board. So now we're going to look at our first example of an alpha decay equation. We have radon decomposing to form polonium plus an alpha particle. We say that an unstable parent nuclei has decomposed to form a more stable daughter nuclei, as well as the particle of radiation. Can you notice a pattern in the orange numbers, the mass numbers? If you look carefully, you can see that the mass numbers add up as though they're in an equation. For example, we simply have 219 equals 215 plus 4. Why am I pointing this out? Well, quite often exam questions won't give you the more stable daughter nuclei, and they will ask you to identify what the element is and maybe what the mass number and proton numbers are. So by seeing the maths behind what's going on, it actually becomes really easy to answer those questions. I'm now going to do the same for the proton numbers so we can see that the same thing is happening there. Here you can see it's the same for the proton numbers, so we have 86 equals 84 plus 2. Nice and simple. If you remember that the mass numbers and proton numbers either side of the arrow are equal, then that gives you a really simple method to be able to identify any missing mass numbers or proton numbers in an exam question. We're now going to take a look at an example so that you can see this simple method in action. So here we have an example of a typical exam question where they're asking you to identify the unknown daughter particle. We're going to write out the mass numbers and proton numbers in simple equations to identify the missing numbers. As you can see, our method makes it easy with some simple algebra to quickly find the unknown numbers. So our unknown mass number must be 235 take 4, giving us 231, and our unknown proton number must be 92 take away 2, giving us 90. Now we've identified our unknown mass number and unknown atomic number, how can we find out the identity of this unknown daughter particle? Well, for this, you're going to need your periodic table. Looking at the periodic table, you need to find the chemical element with the same atomic number as the unknown daughter particle. For example, in this instance, you would be looking at your periodic table to find a chemical element with an atomic number of 90. You should identify this unknown element as thorium. The second type of nuclear decay we're going to look at is beta decay, which occurs when a down quark is converted into an up quark. Here you can see the process of beta decay. We begin with the unstable parent nuclei, and within that unstable parent nuclei, a neutron decays to form a proton and a high energy electron. The high energy electron which is emitted is what we call the beta decay. When representing beta decay with chemical symbols, there are 2 options of notation. You could either write the beta decay using the Greek letter beta, or you could represent beta decay in the form of an electron. In either case, the mass number is 0, as the mass of an electron is negligible, and the atomic charge is -1. Next, we're going to take a look at a beta decay nuclear equation. So here we have an example of a beta decay nuclear equation. Hopefully you're noticing that again there's a simple algebraic pattern in both the mass numbers and atomic numbers. Using this, we can write out some simple math to quickly and easily solve any beta decay equation. We've written out the simple maths looking at the total mass number either side and the total proton number either side, and we can see that it all balances out. Let's take a look at a quick example of using this method to identify an unknown in a beta decay nuclear equation. Here we have an example of a beta decay equation with an unknown unstable parent nuclei. We can use our quick and easy algebraic method to identify the missing mass number and proton number, and we can then use our periodic table to identify the unknown element. So using this method, we've quickly been able to identify that our unknown mass number is 14 and our unknown atomic number is 6. In order to now identify the unknown chemical element, you need to look at your periodic table and identify which element has the proton number of 6. If you look at your periodic table, you should see that is carbon. And for our final type of nuclear equation, we're going to take a look at gamma decay. Alpha decay is a helium nuclei, 2 protons, 2 neutrons. Beta decay is a high energy electron. So what is gamma decay? Is there a gamma particle? Well, not exactly. A gamma ray is a form of electromagnetic radiation. So there are photons, which aren't exactly particles, although wave-particle duality is a whole other topic. Here you can see the process of gamma decay. As with all forms of nuclear decay, we begin with an unstable parent nuclei. This is a high energy nuclei, and when it decays by gamma decay, it's losing some of its energy in the form of gamma rays. As the unstable parent nuclei is losing energy as opposed to any protons, it remains the same chemical element. Let's take a look at an example of a gamma decay nuclear equation. So here we have our example of a gamma decay nuclear equation. Hopefully you're now becoming an expert on our quick and easy method of noticing patterns between mass numbers and atomic numbers. Here you can see our mass numbers and atomic numbers all balance out nicely. Obviously, gamma decay is the easiest form of nuclear decay to recognize when you're looking at nuclear equations, as a gamma ray is just a form of energy, and so it doesn't have any mass or any charge. And it is quick and easy to notice that the parent nuclei and daughter nuclei are exactly the same chemical elements with the same mass numbers and same proton numbers. So if nothing is happening to the mass numbers, nothing is happening to the proton numbers, it must be gamma decay that is occurring. Let's take a final look at our quick and easy algebraic method in action, this time looking at a nuclear decay equation involving gamma decay. In this final example of solving nuclear decay equations, we are actually looking for the type of nuclear decay. I know it's written up here, apologies, but let's just work through the method to make sure it works and reinforce how easy solving nuclear equations actually is. Time for a bit of basic maths. We have a mass number of 0, an atomic number of 0, and so this must be gamma decay. Ta-da! See how easy that was? Nuclear equations may seem annoying and complicated, but they are super easy once you've got that method sorted. Using the algebraic method we've covered, it's quick and easy to solve the nuclear decay equations as long as you remember all of this information. So you better get learning. There you go. Now you have those superhuman powers to help you easily balance nuclear decay equations. Thank you very much for watching this Fierce Physics video about balancing nuclear decay equations. If you found this video useful, hit that thumbs up button below. Make sure you're subscribed to the Fierce Physics YouTube channel. Share this video with your friends if you think it will be helpful for them too. You can follow Fierce Physics over on Instagram for daily tips at Fierce Physics. Until next time, bye!